Hello everyone. Today we'll discuss about the MOS transistor. It stands for metal oxide semiconductor transistor. Silicon, it is a semiconductor, forms the basic starting material for most integrated circuits. It is a group 4 element in periodic table and it forms covalent bonds with 4 adjacent atoms. As the valence electrons of it are involved in chemical bonds, pure silicon is going to be a poor conductor. As I told you, it forms the covalent bonds with 4 adjacent atoms. It is as shown in figure. So here the conductivity can be increased by introducing small amounts of impurities called dopants into the silicon lattice. A dopant from group 5 of the periodic table, such as arsenic, having 5 valence electrons. It replaces a silicon atom in the lattice and still bonds to 4 neighbors, so the fifth valence electron is loosely bound to the arsenic atom. It is as shown in figure B. So the thermal vibration at room temperature is sufficient to free the electron. This results in As plus, that is arsenic ion, and free electron. The free electron can carry current and this is an N-type semiconductor. A group 3 dopant such as boron having 3 valence electrons, which is as shown in figure C, the dopant atom can borrow an electron from neighboring silicon atom, which in turn becomes short by 1 electron. And that atom is in turn can borrow an electron, so the missing electron or hole can propagate about the lattice. The hole acts as a positive carrier, so we call this as a p-type semiconductor. A metal oxide semiconductor structure is created by superimposing several layers of conducting and insulating materials to form a sandwich-like structure. The transistor can be built on a single crystal of silicon, which are available as thin flat circular wafer of 15 to 30 centimeters in diameter. The CMOS technology provides two types of transistors, an N-type transistor which is named as NMOS and a P-type transistor which is named as PMOS. So the transistor operation is controlled by electric field, so the devices are also called metal oxide semiconductor field effect transistors and we name that as MOSFETs, or it can be simply called as FETs. The cross sections and symbols of these transistors are shown in the figure. The A figure figure A shows the NMOS transistor with its symbol and figure B shows the PMOS transistor with its symbol. The difference between the symbols here is only the PMOS transistor will be having a little a small notch for that one at the gate. So the cross sections and symbols that is as shown in figure, and the N plus and P plus regions here indicates heavily doped N or P type silicon. Here each transistor has conducting gate and insulating layer of silicon dioxide, that is SiO2. Also this SiO2, as we know, it is also called as glass, and also the silicon wafer which is named as substrate or body or bulk. You may be you may observe that in the figure it is written as bulk Si in both the figures, right? That is the silicon wafer. We call that as substrate or body or bulk. Here the gates are gates of early transistors were built from metal, so this is named as metal oxide semiconductor, or MOS, right? Even though the gate has been formed from polycrystalline silicon, or simply we call that as polysilicon, the name is still metal. Here we'll discuss about the NMOS transistor. Okay, the first figure, figure A, which is representing NMOS transistor. It is built with P-type body and has regions of N-type semiconductor adjacent to the gate called the source and drain. You can observe in the figure. So at the center, gate is there, and adjacent to it there are source and drain regions. They are physically equivalent and they can be interchangeable. The body is typically grounded usually. So if we come to the PMOS transistor, it is just the opposite of N-type transistor, and it is consisting of P-type source and drain regions with an N-type body. In NMOS transistor, what we were having, N-type semiconductor adjacent to the P-type body was there, and N-type semiconductor adjacent to the gate. There were source and drain. But here in P-type semiconductors, we have P-type source and drain regions for the N-type body. So P-type semiconductors are just opposite of NMOS transistors. Okay. So in both, the gate is going to be the control input. So we'll discuss about the NMOS transistor. It controls the flow of electrical current between source and the drain. Its body is generally grounded, so the PN junction of the source and drain to body are reverse biased. So if the gate is also grounded, then no current flows through the reverse bias junctions and the transistor is said to be in off condition. Suppose if the gate voltage is raised, it creates an electric field that starts to attract free electrons to the underside of SiO2 interface. So the bulk Si and the Si, it is there. You can observe in figure, SiO2 is there and bulk Si is there. So there, in that interface, the created electric field starts to attract free electrons. If the voltage is raised enough, the electrons outnumber the holes, and a thin region under the gate called the channel is inverted to act as an N-type semiconductor. Hence, a conducting path is formed from source to drain and the current can flow. This is the condition for transistor to be in on state. Thus, if we conclude, this thing means the gate of an NMOS transistor is high. When the gate of an NMOS transistor is high, means the transistor is in on condition and there is a conducting path from source to drain. Vice versa, when the gate is low, the NMOS transistor is off and almost zero current flows from source to drain. Next, we'll see about PMOS transistor. And here, as I told you in the beginning itself, it is just the opposite of NMOS transistor, and whatever the operations are there, it is just reversed. Okay, the conditions that we have seen in NMOS transistor, it is just reversed in this case in PMOS transistor. And here the body is held at positive voltage, and also when the gate is at positive voltage, the source and drain junctions are reverse biased and no current flows. The transistor then the transistor is said to be in off condition. And when the gate voltage is reduced, positive charges are attracted to the underside of the Si-SiO2 interface, as I told you in the beginning itself. So Si-SiO2 interface. A sufficiently low voltage inverts the channel, and a conducting path of positive carriers is formed from source to drain. So this is going to be the state where we can call the transistor is an on condition. So PMOS transistor is just opposite of that of NMOS transistor. It is on when the gate is low and off when the gate is high. Next, in the figure you can check the transistor symbols and switch level models, uh, where NMOS and PMOS are shown. So here you can observe that there is a gate, a drain and a source in both the NMOS and PMOS. But the difference here is, in NMOS at the gate nothing is there, and at the PMOS you have a little bubble over there. It is the difference between NMOS and PMOS transistors. So the whole process depends upon the gate, the condition of the gate. When G is 0, what happens in NMOS and PMOS, and when G is equal to 1, what happens in NMOS and PMOS. It is given clearly over here. So in NMOS, when the gate is 0, the drain to a source is just open circuited, which is named as off condition. So when G is equal to 1, that is the gate is high, then we are going to call it is closed circuit, or there will be the connection between the drain and the source. So that is going to be the on condition for NMOS. Uh, it is vice versa in PMOS. So here, when the gate is low, there will be a communication between drain and the source. So there will be a closed circuit, which is named as on condition, and when gate is high, then there will be no communication between the drain and the source, which is going to be the off condition. So we'll discuss about MOS transistor theory in our next class. Thank you.